Hey everybody, welcome back to part 2 of our 3.1 video lesson. So in 3.1, we addressed the concept of scatter plots. We were able to distinguish between explanatory and response variables. We were able to make a scatter plot, and we were able to describe the direction, form, and strength of a scatter plot, as well as identify any unusual features. Now what we're going to be doing in today's lesson is we are going to discuss this concept of correlation. So by the end of this video, we should be able to interpret the correlation. We should be able to understand the basic properties of correlation, as well as how correlation is influenced by outliers. And then we should be able to distinguish between correlation versus causation. Okay? So earlier in part 1, and you can watch the video, it is posted in Schoology, explanatory variables help explain any changes in the response variable, whereas the response variable is the outcome of a study. A scatter plot is just a graphical representation that shows the relationship between bivariate data, or in other words, two variables that are measured on the same individuals. And then when we describe a scatter plot, 4 things that need to be addressed. Direction or association, which is either positive or negative, and we want to include context. The form will either be linear or nonlinear. Strength will either be weak, moderate, strong, or we could say moderately strong, moderately weak if it's somewhere in between. And lastly, any unusual features are any points that drastically differ from the rest of the overall pattern. So what we're going to talk about in this video is the concept of correlation. And we see at its core, we see this word relation. How strongly are these things related to one another? Now, the symbol that we use for correlation is the letter R. By definition, correlation is a value between -1 and 1 that measures the strength and the direction of a linear relationship. Strength and direction. Now, when we see this -1 and +1, think about those as -100% and +100%. That is to say that if we have a correlation of 1, that means that there is a 100% positive relationship between the variables. It's perfect. Whereas if we see a -1, that means that it's a -100%, which still means it's perfect, but it's just in the negative direction. And I'll clarify that in just a little bit. Now, our formula, how do we calculate correlation? It's right here. However, you will never need to calculate the correlation by hand. We will always use our calculator in order to calculate the correlation. And I will tell you how you need to get that set up on your calculator to make sure that that displays. Direction is determined by the sign of R. So again, if R is positive, so if correlation is 0.6, then that means we have a positive correlation. The points typically are going up as X increases. Whereas if R is negative, if our correlation is -0.8, then typically as X goes up, Y goes down. So once again, R values that are closer to -1 and +1 indicate strong relationships. -1 is as strong as it possibly can be. The negative just indicates the direction. And that's, again, a common error that students have. They think 1 is extremely strong or perfectly strong, and -1 is perfectly weak. Not the case, okay? R values closer to 0 indicate weak relationship. Okay, so we're talking if you have an R value of 0.1, that's a lot closer to 0 than it is to 1. Therefore, this is a much weaker relationship. So we want to make sure we understand that. Absolute value is another way to think about it. The larger the absolute value, the stronger the relationship. Now, there are no fixed R values for strength, but there are general ranges. So in other words, how do I know if something is weak? How do I know if something is moderate? How do I know if something is strong? Okay, well, what we said was that values closer to 0 are going to be weak. So Here, you can see in this box here, it says add at least 2 points to this graphing area. So if you remember yesterday, we said a weak relationship looked something kind of like this, just absolute chaos, right? And you can see over on the left-hand side of these 18 points, the correlation coefficient is negative 0.06, right? Very close to 0. But as I start to maybe make them a little more linear, we could see that we are at 0.5. Okay, maybe that's a little bit more moderate in terms of strength. Okay, here again, not the strongest, 0.4, 0.3. Okay, this would be a weaker relationship. But we saw around 0.5 we were starting to get something a little bit more. Okay, and as I just toy with some stuff here, okay, we could see 0.6 is going to kind of be that moderate range. And then this would be a stronger relationship. We can see how close these are, and as I continue to add more points along that line, we can see that that correlation continues to get closer to +1. If I wanted to do the same thing in the negative direction, okay, we can still see that that is a strong relationship, but the correlation is negative. That's simply because of the direction. Okay, so long story short, a weak relationship is going to be roughly when the absolute value of R, and let's do interval, something like this. Roughly, and again, these are no hard and fast rules, but typically if your R value or the absolute value of R is from 0 to 0.3, we're talking about a weak relationship. Then as we continue to advance up the scale here, anything but above 0.3 and maybe up to a 0.7, 0.75, something like that. Now we're talking about a moderate relationship. And then lastly, really anything greater than 0.75, and obviously it cannot exceed 1, that's your strong relationship. Now, that's not to say that if you say a correlation of 0.74 is strong, you'd be wrong, or if you were to say that a correlation of a negative 0.8 was moderate, you'd be wrong. There's certainly flexibility. So I don't want you to spend time trying to memorize these cutoff points or these intervals, because it's not a hard and set rule in the realm of statistics. These are just general guidelines to kind of help influence. What these will help, though, is when you do calculate correlation, you'll be able to address these things right away. What's the direction? Well, if R is positive, then the direction is positive. And if R is negative, the direction is negative. Okay, it'll also be able to address strength, okay, with that scale that we were just discussing. Okay, so we're going to hold off on that fun activity. If you want to click on it, by all means, go ahead. And you can experiment with it a little bit here. But what that one should pull up is a link where it gives you a scatter plot, and then you just kind of guess what the correlation is, and then you work through that, again, just to kind of give you a better sense as to what that is. But what we'll do is we'll proceed here to example 6. Suppose that a PE teacher collected data on students in his class. Some of the variables included are the number of pull-ups done in 1 minute, the number of sit-ups done in 1 minute, and the number of push-ups done in 1 minute, as well as student weight. The teacher then calculated the correlation between the number of pull-ups and each other variable. So we're comparing how many pull-ups they did compared to everything else. Now, the correlations that were found were 0.9 for one variable matching up with pull-ups, negative 0.5 for another, and 0.3 for another. Which correlation goes with each variable, and explain. Okay. So, first one, if we want to match up pull-ups with sit-ups. Okay, that's one pairing. The next one is pull-ups to push-ups. And then our last pairing is going to be pull-ups to weight. And now we have to try to determine, of these three different correlations, which one goes with which. So right away when I look, I see we have a strong relationship, a strong positive. So as the number of pull-ups increases, something else will increase, either the number of sit-ups, the number of push-ups, or the weight. I see that one has a negative relationship, which means as the number of pull-ups goes up, the other would go down. And then lastly, I see a correlation of 0.3, a weak relationship where there really doesn't seem to be a whole lot of relation between the number of pull-ups you can do versus something else. So when I think about these things, I think the first one that's pretty straightforward is the number of pull-ups we can do and the number of push-ups we can do should be pretty strongly correlated in a positive direction because we're working the same set of muscles. Right? When we're doing pull-ups, that's an upper body lift. So we would expect someone who can do a lot of push-ups could probably also do a lot of push-ups. Likewise, someone who can do a lot of push-ups could also do a lot of pull-ups. So we would expect a strong positive correlation there. Both are upper body exercises. Whereas now when I look at this next one, which one would have the negative correlation? Which means as the number of pull-ups goes up, the number of sit-ups goes down, or as the number of pull-ups goes up, weight goes down. And that's probably the better option of the two. Typically, lighter people would be able to do more pull-ups. There's less weight to pull up. Whereas as weight increases, the number of pull-ups that can be done would probably be going down. So we would say this one would be negative 0.5. Because heavier people can probably do less pull-ups. Okay, there's an inverse relationship there. As one goes up, the other goes down. And lastly, that leaves us with R equal to 0.3, a weak relationship. That's got to be pull-ups to sit-ups. And that's because we're working two different parts of the body. The number of pull-ups you can do isn't really going to affect much the number of sit-ups that you can do, but we do see a slightly positive correlation. R is 0.3, positive 0.3, which probably lends itself to people who are more physically fit would probably be able to do more of each. Okay? Because these are different body part exercises. So this is just simply matching correlations and understanding what each one means. So now in example 7, it says to calculate the correlation between, we did height and we did shoe size, and interpret your answer. Now, always include context by using variable names in your answer. So, give me just a second here as I've got to retype this in.
Wanna play?
Oh, these beautiful ads. Alright, so we had 71. And by all means, feel free to fast forward during this part of the video. So then that way you can just catch me at the end once I'm done entering everything. Almost done here if you have not fast forwarded. Alright. So, in order to calculate our correlation, first thing you want to do is you want to make sure that the stat diagnostics are on your calculator. So the way you do this is next to your second button. This should work for most calculators, but not for all, depending on what year or what model you have. So we're going to try the most common version first. Next to your second button is a button that says Mode. Press that. And then if you scroll down towards the bottom, you should see something that says Stat Diagnostics. You want to make sure that Stat Diagnostics is turned on. If that's the case, then you just hit second, quit to go back to your home. If it's not on, turn it on. Now, if it's not, or if you don't have Stat Diagnostics listed there, you have an older model calculator, no big deal. This is how you turn it on. You're going to hit your second button, and then right above the number 0 button, you see that in blue it says Catalog. Hit 0. Catalog is all the different functions for your calculator. Now, we want to check for diagnostic. So without hitting anything else, you can already see that my alpha button, which is in the top left underneath the second button, is highlighted in red. You would just hit your green alpha button, and then, or it should already be selected for you. You want to select the letter D, which is 2 below the alpha button, and then just hit the down arrow until you find, mine's not going to show it because I've got Stat Diagnostics, but you're going to look for the one that says Diagnostics On or Diag On. I think it's Diagnostic On, and then just hit enter. Okay? But by that point, everyone should now have your Stat Diagnostics turned on. So in order to calculate R, you're going to hit Stat Calc, just like where we did our one variable stats, but we are going to choose option 8. It says Lin Reg, which stands for linear regression. We'll talk more about that later on in this unit, but we're going to select option 8, and it's going to ask where is your X data, where's your Y data. So for you, it's probably in list 1 and list 2. I had to enter some other data in. So for me, it's list 5 and list 6. But again, that's for me specifically. You'll probably have list 1 and list 2. Frequency list, leave blank. Store regression equation, leave blank. And what you'll see is a variety of letters. Obviously, for this, we just care about R. We'll talk about what all the other ones mean at a later point. But we can see that R is 0.90. Okay. So calculate the correlation. We would say that R is equal to 0.90. And then always include context by using variable names in your answer. So after we have our correlation, we can interpret that answer. What does that mean? Okay. There is a strong positive relationship. Okay, strong from the sense of the absolute value is close to 1. Positive because this is a positive value. There is a strong positive relationship between height and shoe size. Typically, as one increases, so does the other. Okay, that's how we interpret our answer. Okay, calculate right here, interpret right here. There's a strong positive relationship that's based on the R value between our two variables, okay, giving context. Typically, as one increases, so does the other. Okay. Now, the last couple things that we have are cautions about correlation. First and foremost, correlation does not imply causation. Things can be related to one another without one causing the other. Here's an example. Okay? Ice cream and drowning scatter plot. So ice cream production. Okay? As more ice cream is produced, drowning deaths increase. Right? We can see that. As more ice cream is made, more people die of drowning. The correlation of this is 0.87. That is a strong positive relationship, which means that as more ice cream is made, more people are dying. Now, cause and effect? Certainly not. Right? These two are related. Why are they related? Has to do with temperature. Okay? This was something that we talked about in the last video lesson. Okay, there might be a relationship between two variables that strongly influence both. Okay, in this case, temperature is that lurking variable. As temperature increases, more ice cream is made. As temperature increases, more people are swimming, and that's really what's going on in the background. So yes, there is a strong correlation between ice cream production and drowning deaths, but certainly there is not a cause and effect relationship here. Next, we talked about how correlation, right here in the notes, works strength and direction. Strength and direction. Correlation does not measure form. Correlation does not tell us whether something is linear or not. So an R value close to -1 or 1 does not necessarily mean that the graph is linear, even if it has a strong relationship. So in example 8 here, to kind of show that, it says to sketch a scatter plot using the data in the table below, then calculate its correlation. All right, so I'm going to ask that you pause the video here to put this data into list 1, put this data into list 2, and then use your calculator to make a scatter plot. Once you've done that, go ahead and resume the video. Okay. So if you take a look here, I've got in list 1 our years of 0 to 6. And then in list 2, I've got that population of fish. We can see that it is decreasing as years go by. All right, so as years increase, fish population decreases. We would expect to see a negative correlation between that. And if I make that scatter plot, give me just a second. We can see that this is non-linear. We can see that it's got that curved pattern where it drops off quickly and then it starts to flatten out. Okay. So there's the sketch. Now it says to calculate the correlation. So once again, our steps for calculating the correlation: stat calculate or stat calc, option number 8, linear regression. We're pulling from list 1 and 2, and we can see that our correlation, not surprising, is negative. Okay, negative 0.92. So we have a correlation close to -1. However, this is not a linear graph. Okay? Long story short, correlation tells us strength and it tells us direction. It will not tell us form. Okay? Next, correlation should only be used to describe linear relationships. If our data is not linear, we shouldn't say anything about its correlation value, because correlation is only used for linear relationships. Now, that's not to say that if an R value is close to 0, there is no relationship. It's just saying that there's no linear relationship. So to depict that for us, example 9, sketch a scatter plot using the data in the table below, and then calculate its correlation. So again, I'm going to ask that you pause the video, put this data again into list 1, put this data into list 2, make your scatter plot, and calculate your correlation. Okay. So for me, that data is in lists 3 and 4. So when I make my scatter plot, I'm going to do list 3 and list 4. There we go. And we can see that it's certainly not linear, but this is following a perfect parabolic relationship. Okay. And now if I were to calculate my correlation, on list 3 and list 4, we can see that the correlation, or the R value, is 0. So, just because an R value is close to 0, that doesn't mean that there is no relationship. just means that there's not a linear relationship. Okay. So correlation should only be used to give us information about linear relationships. Okay. Lastly here, correlation is not resistant. Remember that if something is resistant, that means that it's unaffected by extreme values. So since correlation is not resistant, that means it will be affected by extreme values. So notice here in example 10, below is a scatter plot comparing the cost of a tablet to its battery life. The correlation is negative 0.07. That's to say that as cost goes up, battery life goes down. Okay? That shouldn't seem to make too much sense for us. If something's more money, we would expect it to work better or last longer with its battery. So interpret the correlation in this example and explain why that interpretation may not be entirely accurate. So our interpretation is there is a weak negative relationship between cost and battery life. Okay. Now, because this is a weak relationship, we don't want to say something like typically as cost goes up, battery life goes down. Because it's a weak relationship, that really means that there is an inconsistent set of behaviors. Now, again, explain why this interpretation may not be entirely correct. Well, if we just took those two things away, so if I were to make those disappear really quick, then we can see that the rest of our pattern here is actually working in a positive direction, which we would expect. But the reality is we have two outliers here that influence the correlation. Okay? There are two outliers that are expensive and have low battery life that alter an otherwise positive correlation. There are two outliers that are expensive and have low battery life that alter an otherwise positive correlation. And you can use whatever kind of wording you need to. Put it in your own words as long as it makes sense. But that's what's going on here. Okay. Now, lastly here, just some additional facts about correlation. First, correlation requires both variables to be quantitative. Okay, if you remember up here, there is a calculation for correlation, which means if we have categorical data like color, something like that, we can't input calculate or color into these things. So the data must be quantitative in order to do this. Okay, when the data is categorical, we use that word association, which we learned about in chapter 1. Okay, so there's a correlation if it's quantitative data. There's an association if it's categorical data. Next, correlation makes no distinction between the explanatory variable and the response variable. So in other words, that means if we were to flip our x's and our y's, our correlation would not alter. Okay, and I'll just show that really quickly here on the calculator. So if I did the linear regression on list 1 and list 2, where list 1 is the x values and list 2 is the y values. Oh, we froze, so give me a second here. We can see that the correlation is negative 0.924, so on and so forth. If I do this again, but now I say that my X list is list 2, and I say that my Y list is list 1. So if I flip my X and my Y, I again see that the correlation is again negative 0.92. Therefore, correlation makes no distinction. If X and Y switch, the correlation doesn't change. Next, R does not change when we change units of measurement for X or Y or both. Okay, so for example, the correlation of height in inches versus weight in pounds would be the same correlation if we converted the heights into centimeters and the weights into kilograms. Okay, provided that these measurements were taken on the same individuals. So when we change units of measurement, the correlation will not change. Lastly, correlation has no unit of measurement. It is simply a number. It is the result of this calculation right here. So we would not say that the correlation is 0.8 pounds. We would not say that the correlation is negative 0.2 hours. Correlation is a single value from -1 to +1 with no unit of measure that tells us the strength and direction of a relationship. Okay? That is all that we have for 3.1. So now that we've watched part 2 of the lesson, we should be able to interpret a correlation. We should be able to understand the basic properties of correlation, and we should be able to distinguish correlation from causation. Okay, thank you all for watching, and as always, if you have any questions, please feel free to reach out. Have a great rest of your day.